A schematic representation of a typical bridge is represented here. Basically, a bridge consists of superstructure, substructure, and foundation. Let's get to know the components of bridges in this topic. The components of bridges are basically grouped under 4 categories, namely superstructure, substructure, foundation, and auxiliary components. The superstructure is the portion of the bridge above bearings, which directly supports the pedestrian, vehicle, or other transient loads and transfers it to the substructure. The substructure of the bridge transfers the load from superstructure to the foundation. Next is the foundation. It is in direct contact with earth and it transmits loads to the soil strata. All other components which does not come under any of these groups are usually referred as auxiliary components. They include bearings, expansion joints, wearing coat, crash barriers, handrails, curbs, etc. The deformation-induced, creep shrinkage, temperature settlement effects are to be considered. The seismic loads effects, wind load effects, accidental effects are also to be considered based on the structural form adopted. Let us discuss the various types of superstructure. The 4 common types of the superstructure are slab type, girder and slab type, arch type, and truss type. For a slab type superstructure, the solid slab or wired slab is the only constituent of the superstructure. For a girder and slab type, the deck slab longitudinal and cross girders constitute the superstructure. In the case of the box girder, both the deck slab and girder is a composite unit. For arch-type superstructure, the deck slab arches, spandrels, hangers, and cross girders constitute the superstructure. For truss type, the truss members along with the deck slab forms the superstructure. Let's discuss the components of the superstructure in detail. The components of the superstructure depend on the structural form adopted. It usually consists of the deck slab and the longitudinal load-carrying members that span between the piers. The deck slab transfers the load to those longitudinal load-carrying members. The deck slab transfers the load to those longitudinal load-carrying members. We will see the components of superstructure in detail. Let's take a look into various components of superstructure. We will start with deck slab. The deck slab is the structural member which will be in direct contact with the moving loads. Wearing coats are laid on the top of the deck slab to facilitate the movement of vehicles. It is either made integral to act compositely with other members or rests on top of the load-carrying members depending on the structural form adopted. In a conventional girder and slab structural form, the deck slab is made monolithic with the girder and contributes to longitudinal load-carrying capacity. It is mostly made of reinforced cement concrete, RCC. Next, let's move to the longitudinal and cross girders in the bridge. Longitudinal girders are the structural members that span between piers and abutments. It transfers the load from the deck slab to the substructure. They are mostly made composite with deck slabs. The cross girders prevent the lateral torsional buckling of girders, redistribute the loads between girders and transfer load to bearing in case of indirect supports, where girders are supported on diaphragms, or to substructure in case of integral bridges. Girders, as in the case of superstructure, are mainly designed to cater the gravity loads due to fact that they span horizontally. Girders are made of RCC, PSC, or steel, depending on the structural form adopted. Next, let us look into various components in substructure. Substructure is mainly composed of piers, abutments, and wing walls, or written walls. The substructure transmits the load to the foundation, both vertical loads and horizontal loads. The vertical loads are mainly due to the gravity loads, and the horizontal loads are due to seismic loads, wind loads, braking traction, etc. It retains the earth in the approaches as in the case of abutments and wing walls. The choice of type of substructure depends mainly on the structural form and foundation type adopted, as well as the site-specific features like geotechnical and hydrological aspects and the functional or geometric requirements of the bridge. It is usually made of reinforced cement concrete, but it is occasionally made of pre-stressed concrete or steel. Piers and abutments are kept at distinct intervals to permit the flow of water or movement of vessels, vehicles, trains, etc., below. Next, let's discuss the components of substructure. The substructure is mainly composed of piers, abutments, and wing walls. Let's first discuss the pier of a bridge. Piers are usually composed of a pier cap or bed block that directly supports the superstructure with bearings in this case of simply supported or continuous systems, or without bearings in the case of integral systems. Piers can be wall type, hammerhead type with equal cantilevers, cantilever type with asymmetric cantilevers, or portal type. The bed block is provided for wall-type piers to distribute the concentrated loads from the superstructure uniformly to the pier stem. The pier cap is provided when the pier stem is not provided for the full weight of the carriageway for economical or structural reasons. It can be cantilever type or portal type. Usually, the design of the pier cap is governed by vertical bending. The next important component is the pier stem below the pier cap or bed block, which rests on the top of the foundation and transfers the load to the sim. The design of pier stems are usually governed by the lateral loads, both longitudinal and transfers, arising from wind, seismic braking, traction, centrifugal, deformation-induced loads due to creep, shrinkage, temperature, settlement, etc. The total width of approaches are usually greater than the width of the bridge. If so, the earth beyond the abutments has to be retained by wing walls or by the provision of stone revetments. If the width of the approaches are same as that of the bridge or if stone revetment are provided, the approaches are to be laterally retained by means of structural RC walls called return walls. Return walls are usually provided till the extent of the foundation of the abutment in the longitudinal direction. It is basically earth-retaining walls and is hence designed for lateral bending due to the earth pressure. Provisions like weep holes and filter media are usually provided for these walls to allow water to seep through and hence avoid designing of the water pressure due to the retained water. Let's move on to the next component, that is the foundation. The foundation transfers the load from substructure to the founding strata, which is either the bedrock or soil. Foundations may be broadly classified into shallow and deep depending on the depth of foundation. Bridge foundations are usually of three types. Open foundation, which is type of shallow foundation, pile foundation, which is a deep foundation, well foundation, which is also a deep foundation. The choice of function types depends primarily on the following factors: magnitude and nature of loads from the substructure. Geotechnical aspects like bearing pressure, bed profile, soil characteristics, founding data, etc. Hydrological aspects like scouring. Constructability aspects, type of superstructure and substructure. Foundations are designed to distribute the loads to such an extent that there won't be any failure or unnecessary settlement of the founding strata. Let's look into different types of foundation. First we will discuss about the open foundation. It is a type of shallow foundation where the loads from substructure is transferred to the founding strata at a shallow depth from the existing ground level. This type is adopted when the loads are lesser and the safe bearing capacity of founding strata is sufficiently high at the shallow depth. The founding strata could either be soil founded below the scour depth or rock. Footings are checked for structural adequacy and base pressure as well as for stability against overturning and sliding as well. Uplift and base pressure is not allowed for foundations in soil. For rocks, the contact area can be as low as 67%. A type of deep foundation which usually offers high geographical capacity and usually provided in groups. Most common type of bridge foundation, as the loads coming from the substructure are usually high. The piles could drive the bearing capacity from end bearing or friction or the combination of both. Piles are usually bored cast in situ or driven precast piles. A thick pile cap is usually provided below substructure to uniformly distribute loads between piles. Piles are so spaced, usually 2 to 3 times of the pile diameter that influence area of individual piles does not overlap. Let's move on to the next type of deep foundation, that is the well foundation. Well foundation is a type of deep foundation characterized by large diameter hollow shafts, where the geotechnical capacity is derived from frictional resistance and end bearings. Generally, the hollow shaft called steining is cast in parts and sunk through the strata by progressively removing earth through dredged hole, hollow portion. A well cap is provided below substructure to uniformly distribute loads between throughout steining. Usually adopted when the capacity requirement is high and provision of piles is uneconomical. Ideal under scouring condition when lateral loads are higher. Bearings play a major part in the deck articulation, which in turn significantly influences the design. Bearings are classified as fixed, free, guided, pin, etc., based on the nature of movement it allows. Bearings are classified as elastomeric, PTFE, also known as polytetrafluoroethylene, spherical, metallic, etc. Bearings are designed to transfer either or both vertical and lateral loads from a superstructure while themselves undergoing rotations and movements. Appropriate type and arrangement of bearings shall be selected on the basis of geometry and type of superstructure, nature and magnitude of vertical and horizontal loads, direction and magnitude of rotation and translator movements. Practical aspects for replacement of bearings. Since the design life of bearings is usually less than the design life of a bridge, expansion joints shall be robust, durable, watertight and replaceable. Expansion joints can be classified according to their materials, allowable movements, and mechanisms such as filler boards, strip seals, omega seals, modular strip seal, and finger joint. The type of expansion joints shall be decided based on direction and magnitude of rotation and translatory movements of the superstructure and by considering the inspection, maintenance, and replacement aspects. Barrier provided at the side of the carriageway designed to reduce the risk of serious accidents by guiding the errant vehicle back on the road. Crash barrier shall be of the following types: flexible, semi-rigid, and rigid. Flexible barrier, these are yielding types such as wire rope fencing. Semi-rigid barrier, these offer required resistance to errant vehicles by deflection of the longitudinal member to an acceptance limit. Example, metal beam crash barriers. Rigid barrier, these do not deflect on impact and hence take full severity of impact. Example, reinforced concrete crash barrier. Handrails and parapets, the bridge railings or parapets shall include the portion of the structure erected on and above the curb or deck for the protection of pedestrians or cyclists from falling over. Rails or parapets may be provided separately or in combination where railings are attached on top of the parapets. Our parapet may be of the following type: steel rolled section, tubular steel, cast in situ concrete, and precast concrete. Parapets usually serve a dual purpose in acting as noise barriers. In metros or rail-based transit systems, parapets usually serve as emergency walkways. Curb are a line of raised concrete section forming an edge between carriageway and railing or footpath or median. Curb shyness is the imaginary distance by which the driver would generally keep his vehicles away from the curb in order to avoid brushing with the curb. Shyness is usually 500 mm. Safety curb is a curb having a width of at least 750 mm for occasional use by pedestrians in lieu of a footpath. Curbs could be surmountable or unsurmountable for vehicles and should be designed accordingly. Approach slab is a transition slab of reinforced concrete laid on immediate approaches to a bridge, with one end resting on a dirt wall or abutment. It is common for approach embankments to settle more than abutments. This may cause discomfort to moving traffic as well as make the bridge more susceptible to damage due to impact loads. To mitigate this issue, approach slabs are used to transition the riding surface from the approach to the bridge deck. When the approach settles, the approach slab's end resting on the approach gradually launches itself, thereby forming an inclined ramp-like axis. Effectiveness of approach slabs increases with length. A dirt wall is a vertical wall projecting from the abutment cap to prevent the spill of earth or pavement materials and also to support the approach slab. Dirt walls are usually designed for the lateral earth pressure from the retained approaches and the vertical loads from the approach slab and design vehicles. Need not be considered to cater for earth pressure if reinforced earth walls are provided behind dirt walls. Dirt walls are usually made of reinforced cement concrete. The length of a bridge is usually represented by the distance between the faces of dirt walls on each abutment. Play video starting at 8:7 and follow transcript 8:07. Noise barriers, it is provided at selected sensitive locations, example near hospitals, academic institutions, etc. to mitigate the impact of excessive noise generated by road traffic. Sound-absorptive or reflecting panels are placed between the source of noise, that is, moving traffic, and sound-sensitive receivers to reduce overall noise levels. Placed usually on top of the parapets. Typically, they can reduce noise levels by 5 to 10 decibels. RC walls, polycarbonate panels, aluminum panels, etc., are usually adopted as noise barriers. Noise barriers are very relevant in the case of concrete wearing coat where the pavement noise is higher. Bearings are placed over the bearing pedestal to transfer loads to the pier cap. Bearings transfer heavy concentrated loads to the substructure and cause tensile stresses in the vicinity of the bearing zone. The reinforced concrete, that is, RC pedestals are designed to nullify these effects so that the concentrated load is distributed to uniform vertical pressure throughout the pedestal area without causing any undesirable tensile stresses in the pier cap. Pedestals are also helpful in achieving the cross-slope for superstructure drainage. As per IRC 5, pedestal heights range from 150 to 500 millimeters. Play video starting at 9:46 and follow transcript 9:46. Seismic restrainers or reaction blocks. These are vertical concrete upstands from the pier cap provided to transfer the seismic forces directly from the superstructure to the substructure. A vertical elastomeric bearing is usually provided between the bearing surfaces, that is, the superstructure, and restrainers to distribute the bearing pressure uniformly. Restrainers are usually not intended to transfer any forces other than seismic forces. They are designed for the full seismic force, assuming bearings do not partake in any part of the seismic force used as an additional safety measure in seismic zones 4 and V, even if bearings are designed for seismic forces. Bearings are placed over the bearing pedestal to transfer loads to the pier cap. Bearings transfer heavy concentrated loads to the substructure and cause tensile stresses in the vicinity of the bearing zone. The reinforced concrete, that is, RC pedestals are designed to nullify these effects so that the concentrated load is distributed to uniform vertical pressure throughout the pedestal area without causing any undesirable tensile stresses in the pier cap. Pedestals are also helpful in achieving the cross-slope for superstructure drainage. As per IRC 5, pedestal heights range from 150 to 500 millimeters. Play video starting at 9:46 and follow transcript 9:46. Seismic restrainers or reaction blocks. These are vertical concrete upstands from the pier cap provided to transfer the seismic forces directly from the superstructure to the substructure. A vertical elastomeric bearing is usually provided between the bearing surfaces, that is, the superstructure, and restrainers to distribute the bearing pressure uniformly. Restrainers are usually not intended to transfer any forces other than seismic forces. They are designed for the full seismic force, assuming bearings do not partake in any part of the seismic force used as an additional safety measure in seismic zones 4 and V, even if bearings are designed for seismic forces.